Part 1. The clock you never noticed. There is a clock running in the room where you are sitting right now. Not the one on your phone, not the one on the wall. A different clock. One you did not put there, one you cannot touch, one you did not even know existed until someone thought very carefully about the nature of gravity and realized, with a kind of quiet intellectual horror, that time itself is not a fixed, immutable river flowing at the same rate everywhere. It is something softer than that, something that bends. Right now, if you are sitting on a lower floor of a building, your clock, every atom in your body, functioning as an infinitesimally precise timekeeper, is running ever so slightly slower than the clock of someone standing on the roof above you. Not because their clock is broken, not because yours is, because the gravitational field you are sitting in is fractionally stronger than theirs, because the Earth's mass is pulling at you with a slightly tighter grip than it is pulling at them, and because gravity, as it turns out, does not merely attract matter. Gravity shapes time itself. This is not science fiction. It is not philosophy. It is not an intellectual metaphor dressed up in poetic language. It is one of the most precisely tested and rigorously confirmed predictions in the entire history of physics. Engineers had to account for it when they designed the satellites that give your phone its GPS signal. Physicists measured it directly in a building at Harvard University in 1960, using nothing but gamma rays and iron atoms and a 22-meter vertical shaft. And the difference between the time experienced at the bottom of that shaft and the top of it was real, measurable, and exactly as large as Albert Einstein had predicted it would be. The idea that gravity bends time is one of those concepts that sounds almost mystical when you first hear it, but becomes, the longer you sit with it, one of the most natural and inevitable conclusions in all of science. Once you understand the chain of reasoning that leads there, you feel less like you have learned a strange fact about the universe, and more like you have been shown something that was hiding in plain sight all along, something that the universe was doing constantly, at every scale, all around you, while you were busy assuming that time was simply running. So let us follow that chain of reasoning together, not rushing, not skipping steps, starting where Einstein started, with a simple and devastating question about what gravity actually is, and arriving somewhere that changes how you think about every second you will ever experience. Before we do that, I want you to hold one number in your mind, one number that anchors the whole story. The GPS satellites orbiting the Earth right now, the ones giving your navigation app its directions, orbit at an altitude of about 20,200 kilometers above the surface. Up there, the gravitational field of the Earth is considerably weaker than it is at sea level, and because of that, the onboard atomic clocks on those satellites run faster than identical clocks on the ground. Not by much. By approximately 45 microseconds per day, 45 millionths of a second, gained every single day, compared to the clocks we keep down here. If the engineers who designed GPS had ignored that effect, if they had said, time is time, a clock is a clock, they all run the same, then within a single day, the GPS system's position estimates would drift by roughly 10 kilometers. Within a week, it would be useless. Every phone in the world giving wrong directions. Every airplane relying on satellite navigation flying blind. Every automated system that depends on precise timing, slowly drifting out of sync with reality. They did not ignore it. They built the relativistic corrections directly into the satellite clocks before launch. They deliberately slowed the oscillation frequency of the onboard clocks so that once those clocks reached their orbital altitude and began experiencing weaker gravity, the combination of the two effects would make them keep pace with clocks on the ground. Your phone's GPS works because the engineers who built the satellites understood that gravity bends time. That is the world we actually live in. That is how real the effect is. Not abstract, not theoretical. Embedded in the infrastructure of everyday life. Running invisibly in the background every time you let a map application tell you which road to turn onto. Now let us understand why. Drop something and watch it fall. You have done this 10,000 times. A pen rolls off a desk. An apple drops from a branch. Water finds its way to the lowest point. You have spent your entire life watching things respond to gravity, and at some level, it has become so familiar that you stop noticing how deeply strange it actually is. Gravity reaches across empty space and pulls things together without touching them. It acts on everything. It cannot be blocked or shielded. There is no gravity-proof material. You cannot turn it off. You cannot stand to one side of it. Every particle of mass in the universe is simultaneously pulling on every other particle of mass in the universe, right now, across whatever distance separates them, with a force that falls off as the square of that distance, but never actually reaches zero. That is Newton's description. And for most practical purposes, it is extraordinary. It predicts the orbits of planets with remarkable precision. It describes the trajectory of a thrown ball to within measurement error. It built the foundation of classical mechanics, which built the foundation of the industrial world, which built the civilization you are sitting in. Newton's gravity works. It works so well that for over 200 years, almost nobody seriously questioned whether it was telling the full story. But Newton himself never explained what gravity actually was. He described it with mathematical precision. He did not explain its mechanism. He gave it a formula and left the underlying reality alone. He said, famously, that he would feign no hypotheses about what gravity was. He knew it reached across space. He did not know how. And there was another thing Newton never questioned. He assumed, along with everyone else who had ever thought about it, that time was a universal constant, that it flowed at the same rate everywhere. That a second in London was a second on the moon was a second at the edge of the solar system, all identical, all running in perfect lockstep with each other, all part of an absolute background clock against which the universe's events unfolded. That assumption felt so obviously true that it barely registered as an assumption. It felt like a statement about the nature of reality, so fundamental that questioning it would be like questioning whether numbers have meaning. Albert Einstein questioned it. And the universe, when tested with extreme precision, confirmed that Einstein was right and the assumption was wrong. Time is not universal. It is not absolute. It does not run at the same rate everywhere. It is influenced by motion, and it is influenced by gravity. Objects deeper in a gravitational field experience time more slowly than objects farther from the source of that gravity. The difference is tiny in the weak gravitational fields of everyday life. It becomes enormous near the kinds of masses the universe generates at its most extreme, the collapsed remnants of dead stars, the supermassive black holes lurking at the centers of galaxies. But it is always there, always real, always changing the pace at which your clock ticks, depending on how deep in a gravitational field you happen to be sitting. That is the idea we are going to explore in this video, from its origins in Einstein's early thought experiments, to its experimental confirmation on Earth, to its practical effects on the technology we use every day, to its most extreme manifestations in the most violent and exotic objects the universe has produced. Settle in. This is one of the stories that physics tells best. And before we go further, drop a comment below and let us know where in the world you are watching from and what time it is there. There is something fitting about comparing notes on time in a video about how time itself is not what we thought it was. Hit subscribe if you have not already. Now let us keep going. Part 2. Newton's perfect machine and Einstein's radical vision. To understand why gravity bends time, you first need to understand what Einstein was arguing against, what the old picture of reality looked like, why it was so deeply satisfying, and why, in the early years of the 20th century, the cracks in it started to show. Newton's universe was a clockwork, an extraordinary, elegant, profoundly satisfying clockwork. It had 3 laws of motion. It had the inverse square law of gravitation. It had absolute space, an invisible, immovable scaffolding against which all motion could be measured. And it had absolute time, a universal river flowing identically everywhere at once, the same tick marking the same instant for every object in the universe simultaneously, regardless of where those objects were, how fast they were moving, or what gravitational forces they were subject to. In this universe, simultaneity was a simple fact. 2 events either happened at the same time or they did not. And any observer, anywhere, using any method of measurement, would agree on the answer. Time was time. It was the same everywhere. It was outside the physical world, not part of it. For over 2 centuries, this picture worked. It was not just approximately right. In every experimental context that existed before the late 19th century, it was exactly right, as far as anyone could tell. Clocks everywhere seemed to run at the same rate. There was no experimental reason to doubt that they would always do so. Then 2 things happened that cracked the foundation. The first was a failed experiment. The second was a brilliant young clerk in a Swiss patent office who spent his spare time thinking about what it would look like to ride alongside a beam of light. In 1887, the American physicists Albert Michelson and Edward Morley performed a careful experiment intended to detect the motion of the Earth through what was then assumed to be a medium called the luminiferous ether, the substance through which light was thought to propagate the way sound propagates through air. The reasoning was simple. If the Earth moves through the ether, then light traveling in the direction of that motion should travel at a different speed, relative to an observer on Earth, than light traveling perpendicular to it, for the same reason that a swimmer moving against a current covers ground more slowly than a swimmer cutting across it. Michelson and Morley found no such difference, at all, in any direction. The speed of light was the same regardless of the direction of measurement and regardless of the Earth's motion. This result was so unexpected and so clean that it became one of the most consequential null results in the history of science. Something was fundamentally wrong with the picture. Enter the young patent clerk, Albert Einstein, in 1905. He was 26 years old, working in Bern, and he had been thinking for years about a question that had haunted him since he was a teenager. What would it look like if you could catch up to a beam of light? What would you see if you rode alongside a light wave at the same speed the light was traveling? According to Maxwell's equations, which described electromagnetism with extraordinary success, a light wave is an oscillating electromagnetic field. But if you were moving alongside it at the speed of light, the oscillation would appear frozen. A frozen electromagnetic wave is not something Maxwell's equations permit. The mathematics does not produce a static electromagnetic field of that form. There was a contradiction. Einstein's insight was to take seriously what this contradiction implied. If riding alongside a light wave produces a contradiction, perhaps the error is in the assumption that you could catch up to light at all. What if the speed of light was a universal constant, the same for every observer, in every reference frame, regardless of how fast that observer was moving, relative to the source of the light? This seemed absurd. If you are moving toward a light source at 100,000 kilometers per second, surely the light coming from that source reaches you at 300,000 plus 100,000 kilometers per second. Just as the speed of a ball thrown from a moving train adds to the train's speed when viewed from a stationary platform. That is how everything else works. That is how common sense says it should work. But Einstein said no. The speed of light is always the same. Not approximately, exactly. Every observer measures light traveling at precisely the same speed, regardless of that observer's own motion. And then he worked out what this requirement forced upon the rest of physics. If the speed of light must always be the same for every observer, then the things we thought were fixed, space and time, could not be fixed. They had to bend and stretch to accommodate the constant speed of light. Different observers in different states of motion would disagree about distances and about durations. 2 events that appear simultaneous to one observer might not appear simultaneous to another. Time was not absolute. Space was not absolute. The only thing that remained constant was the speed of light. The tool Einstein used to make this concrete was a thought experiment involving an imagined clock made of light. Picture 2 perfectly parallel mirrors facing each other. Between them, a single photon bounces back and forth. Every time the photon hits one mirror, that is 1 tick of the clock. The clock measures time by counting the bounces. Now imagine this light clock moving sideways at high speed relative to you. The photon still bounces between the mirrors, but from your perspective, it is no longer traveling straight up and down. It is traveling diagonally, tracing out a V shape as the mirrors move forward, while the photon is in transit. The diagonal path is longer than the straight up and down path, but light always travels at the same speed, So if the path is longer, each tick must take longer. The clock runs slowly. Not because something is wrong with the clock, not because the photon is slowed down, because time itself, in the reference frame of the moving clock, passes more slowly than time in your reference frame. The clock is recording less elapsed time per tick. If that clock were attached to a biological organism, that organism's cells would divide more slowly, its heart would beat more slowly, its brain would process information more slowly, it would age more slowly. Everything in the moving reference frame runs slow, not because something broke, but because time is not universal. It is personal, it is local. It runs at different rates for different observers, depending on their relative motion. This effect is called time dilation, and it is not a small, barely detectable correction to an otherwise solid reality. At speeds approaching the speed of light, the effect becomes dramatic. A traveler moving at 99% of the speed of light would experience time at roughly 1/7 the rate of a stationary observer. A traveler moving at 99.99% of the speed of light would age roughly 1/100th as fast as someone standing still. The faster you move through space, the slower you move through time. In 1905, this was the special theory of relativity. Special because it applied to a special case. Observers moving at constant velocity relative to each other, with no acceleration and no gravity involved. It was an extraordinary achievement. It overturned everything Newton had said about space and time. It established that they are not separate, fixed backdrops against which physics plays out. They are one unified thing, space-time, a four-dimensional fabric that is not rigid but flexible, that distorts and warps depending on motion. But Einstein was not satisfied. He knew that special relativity was incomplete. It said nothing about gravity. It applied only to observers moving at constant velocities, and the universe is full of acceleration and gravity. Completing the picture would take him 10 more years of some of the most grueling mathematical work in the history of physics. And it would lead him somewhere Newton had never gone, to the realization that gravity was not a force at all, but a curvature of space-time. And that curvature, like the velocity-based time dilation of special relativity, affected the passage of time. The key to getting there was an idea so simple that Einstein reportedly described it as the happiest thought of his life. He was sitting at his desk in the patent office and imagined what it would feel like to fall freely, with no floor beneath him, no ground to catch him, and he realized something extraordinary. In free fall, you feel weightless, you feel no gravity. A person in free fall is, locally and momentarily, in the same physical situation as a person floating in empty space, far from any gravitational source. Gravity, in the reference frame of a freely falling observer, disappears. This is the seed of the equivalence principle, and it pointed Einstein toward the general theory of relativity. Part 3. The elevator that changed everything. The thought experiment that unlocked the general theory of relativity involved an elevator, or rather, a sealed room that could be either an elevator or a room sitting on the surface of a planet, and the impossibility of telling which. Here is the setup. Imagine you wake up inside a sealed, windowless room. You have no idea where you are. You feel a weight pressing down on you, some force pulling you toward the floor. There are two possible explanations. Either the room is sitting on the surface of a planet and gravity is pulling you down, or the room is in empty space, far from any massive body, and is accelerating upward, a rocket underneath it pushing it forward with exactly the force that would mimic gravity. Einstein's question was, is there any experiment you could perform inside that room that would tell you which of those two situations you are in? The answer, as far as he could determine, was no, not in principle, not with any measuring device, not with any physical test conducted within that small room. A ball dropped inside the gravitational room falls to the floor at the same rate as a ball dropped inside the accelerating room. A scale shows the same reading. Light bending through the room follows the same curve. Every physical effect that gravity produces is identically reproduced by acceleration, and vice versa. The two situations are not merely similar, they are physically equivalent. This is the equivalence principle, and it was the conceptual foundation that Einstein built the general theory of relativity upon. Einstein himself called it the most fortunate thought of his life, the thing that launched him toward the theory that gravity is the curvature of space-time itself. The equivalence principle implies something striking. If gravity and acceleration are truly indistinguishable, then anything acceleration does to physics, gravity must also do. And acceleration, as Einstein already knew from special relativity, does something to time. An accelerating observer experiences time differently from a non-accelerating one. Therefore, gravity must do the same. A gravitational field must alter the rate at which time passes. Einstein worked this out quantitatively in 1911, 4 years before he completed the full theory. Using only the equivalence principle and his previous work on special relativity, he showed that light climbing upward in a gravitational field loses energy and frequency, like a ball thrown upward slowing as it climbs. If light loses frequency, it loses energy. But this frequency shift is also, from the right perspective, a statement about time. A lower frequency means fewer oscillations per second. Fewer oscillations per second means time is running more slowly at the source of the light. A clock at the bottom of a gravitational field runs more slowly than a clock at the top. The physical reasoning is easier to follow through the elevator thought experiment. Imagine your sealed room is being accelerated upward in empty space. Light is shining upward from the floor to the ceiling. As the light travels upward, the room continues to accelerate. By the time the light reaches the ceiling is moving away from the source at a slightly higher velocity than the source was moving when the light was emitted. This is a Doppler effect. The receiver is moving away from the source during transit, so it receives the signal at a lower frequency. The light is redshifted. By the equivalence principle, the same must happen in a gravitational field. Light traveling upward against gravity is redshifted. It arrives at a higher altitude with less energy and a lower frequency than it had when it left the ground. This is gravitational redshift. But here is the subtlety that connects redshift to time dilation. Frequency is the number of oscillations per second. If a beam of light carries some frequency as a kind of signature, a specific number of wave crests per second emitted by a source, and that frequency decreases as the light climbs upward, then the receiver at the top is counting fewer wave crests per second than the source emitted. From the receiver's perspective, the source appears to be running slowly. If the source were a clock ticking once per oscillation of the light, the receiver would see the clock ticking more slowly than it actually ticks in its own local frame. Equivalently, time runs more slowly at the bottom of a gravitational well than at the top. A clock at the ground floor of a building ages more slowly than an identical clock on the roof. Not because anything happened to the clock, not because it is broken or disturbed, because the geometry of space-time itself, shaped by the Earth's mass, means that time runs at slightly different rates at different heights. The reasoning worked both ways. Light falling downward in a gravitational field gains energy and frequency. It blue shifts. The mirror image of the redshift light experiences climbing upward, and both effects follow directly from the equivalence principle alone, without needing the full machinery of general relativity. But Einstein knew that the equivalence principle, by itself, was only an approximation. It worked perfectly in small, localized regions of space, inside a small elevator where the gravitational field could be treated as uniform. In the real universe, gravitational fields are not uniform. They point in different directions from different positions, converging toward a central mass. Two objects in free fall toward the same center are not truly in identical situations. They are converging. They feel tidal forces that pull them toward each other, and those tidal forces are the signature of real space-time curvature, something that cannot be removed by choosing a reference frame. To handle this, Einstein needed a new mathematical framework. He needed a way to describe how gravity worked, not as a force acting across space, but as a geometric property of space-time itself. He found that framework in Riemannian geometry, the mathematics of curved surfaces, extended to 4 dimensions. It took him from 1907 to 1915 to complete the work. The field equations of general relativity, published in November 1915, describe how the distribution of mass and energy in the universe curves space-time, and how that curved space-time in turn dictates how matter and energy move through it. The key conceptual shift was this. In Newton's picture, gravity was a force. Masses attracted each other across empty space, and objects fell toward massive bodies because they were pulled. In Einstein's picture, there is no force. Massive objects warp the geometry of space-time around them. What we experience as gravity is simply the natural motion of objects following the straightest possible paths, called geodesics, through that curved space-time. The Earth does not orbit the Sun because the Sun is pulling it. The Earth follows the straightest path available to it through a space-time that has been curved by the Sun's mass. It is the curvature that gives the illusion of force. And because space-time includes time as one of its 4 dimensions, the curvature of space-time that creates gravity also curves time. Near a massive object, where space-time curvature is strongest, time runs most slowly. Farther away, where the curvature is gentler, time runs faster. The relationship between them is exact and mathematically precise, described by the metric of the Schwarzschild solution, which describes the space-time geometry surrounding a non-rotating spherical mass. For a practical intuition, think of it this way. You are embedded in space-time. You move through it constantly, even when you are sitting perfectly still, because time is one of the dimensions you are always traversing. The total speed at which you move through space-time is fixed, always equal to the speed of light. This is one of the deep results of relativity. If you are moving through space at high speed, you are using up some of your space-time velocity in the spatial directions, which means you move more slowly through the time dimension. That is the special relativistic time dilation from motion. Gravity works differently but achieves a similar result. A massive object curves space-time in a way that tilts the time dimension, pointing it partially into the spatial dimensions. Objects closer to the massive body have their time direction tilted more severely. Less of their space-time velocity is going into pure time, so they age more slowly. They experience less elapsed time for the same coordinate distance traveled. Their clocks run slow. This is not a metaphor. This is not an analogy dressed up to sound profound. This is the actual geometric structure of the universe, tested with atomic clocks, confirmed in experiments on 4 continents, built into the engineering specifications of satellites, measured with such precision that we can detect time dilation across a vertical separation of less than 1 meter here on Earth. Einstein predicted it in 1911 with his early work and refined it in 1915 with the full theory. And then the world had to wait for the instruments to become sensitive enough to confirm it. The wait ended in a Jefferson Physical Laboratory building in Cambridge, Massachusetts, in the spring of 1960. Part 4. The Harvard Tower and the First Proof. There is a building at Harvard University with a tower that played a central role in one of the most elegant and precise experiments in the history of physics. The Jefferson Physical Laboratory, a building that has housed important scientific work for over a century. And in 1960, 2 physicists, named Robert Pound and Glenn Rebka, used a 22.6-meter vertical shaft in that building to do something that had never been done before. They measured the effect of gravity on the flow of time. The problem they were solving was subtle. Einstein's prediction for the gravitational redshift of light, the slowing of light's frequency as it climbs against a gravitational field, was well established theoretically by 1960. The astronomical evidence was suggestive. Light coming from the surfaces of white dwarf stars, objects with roughly the mass of the Sun compressed into a sphere the size of the Earth, was redshifted in ways consistent with the gravitational time dilation those extreme surface gravities would produce. But astronomical measurements were inherently imprecise. There were too many confounding factors: temperature gradients in the stellar atmosphere, pressure broadening of spectral lines, uncertainties in the mass and radius of the star. A controlled, terrestrial experiment, where all the variables were known, where the geometry was fixed, and where the effect could be measured directly. The problem was that Earth's gravitational field is weak. The gravitational time dilation between the ground floor and the roof of a tall building is an almost inconceivably small number. For a height difference of 22.6 meters at Earth's surface, the fractional frequency shift of light climbing that distance is approximately 2.5 times 10 to the negative 15, that is 2.5 quadrillionths. A shift so tiny that measuring it with any pre-1960 technology was simply impossible. What made the Pound-Rebka experiment possible was a discovery made just 2 years earlier by Rudolf Mossbauer, a German physicist who would go on to win the Nobel Prize for it. Mossbauer discovered that when certain atomic nuclei embedded in a rigid crystal lattice emit or absorb gamma rays, they can do so without any recoil. Normally, when a nucleus emits a photon, it recoils slightly, the way a gun kicks back when it fires a bullet. This recoil takes a small amount of energy from the emitted photon, and that energy is taken from the photon's frequency. If you then want to use that photon to excite an identical nucleus, the photon's frequency will be slightly too low. It will not be absorbed. But Mossbauer showed that in a crystal lattice, the recoil can be shared across the entire crystal. The effective mass of the recoiling object becomes the mass of the whole crystal, rather than the mass of a single nucleus. The crystal is so much heavier than a single nucleus that the recoil velocity is effectively zero. The emitted photon retains essentially all its energy. Its frequency is sharply defined, precisely matching the resonant absorption frequency of identical nuclei. This is the Mossbauer effect, and it made possible the measurement of frequency shifts so small that they had previously been invisible. Pound and Rebka chose to use iron-57 as their source material. Iron-57 emits gamma rays with an energy of 14.4 thousand electron volts. These gamma rays, thanks to the Mossbauer effect, had a line width so narrow that a frequency shift of a few parts in 10 to the 15th, exactly the size of the gravitational redshift over 22.6 meters, was detectable. The experimental setup was straightforward in principle and demanding in execution. A radioactive iron-57 source at the bottom of the vertical shaft emitted gamma rays upward. A detector, an identical iron-57 absorber at the top of the shaft, would absorb those gamma rays only if their frequency matched the resonant absorption frequency of the iron-57 atoms. If the gamma rays were gravitationally redshifted by the time they climbed 22.6 meters, their frequency would have dropped, and the absorber at the top would not absorb them as efficiently. To measure this shift precisely, Pound and Rebka used a clever trick. They mounted the gamma ray source on a loudspeaker cone that could be made to oscillate up and down at precisely controlled velocities. By moving the source at carefully calibrated speeds, they could introduce a controlled Doppler shift into the emitted gamma rays, shifting their frequency up or down by a known amount. By scanning through velocities and measuring the absorption rate, they could determine exactly what Doppler shift was needed to compensate for the gravitational redshift. That compensating velocity then told them the size of the gravitational redshift. They had to deal with temperature effects that were surprisingly important. Even a temperature difference of 1 degree Celsius between the source and the absorber introduced a shift in the thermal vibrational state of the iron nuclei that was comparable to the gravitational effect they were trying to measure. They painted the source black and the absorber white to minimize temperature gradients. They monitored temperatures throughout the experiment with extraordinary care, taking measurements with thermometers positioned at multiple heights in the shaft. They ran the experiment both with the source at the bottom and the detector at the top, and then flipped the arrangement, placing the source at the top and the detector at the bottom. In one configuration, the light was climbing upward and should be redshifted. In the other, it was falling downward and should be blue shifted. By comparing both configurations, they could separate the gravitational effect from any systematic instrumental biases. When the results came in, they matched Einstein's prediction to within 10% accuracy. Within a few years, Pound and his student J.L. Snyder refined the experiment and confirmed the prediction to within 1%. The gravitational time dilation was real. The photons climbing 22.6 meters against Earth's gravity were measurably redshifted. Time ran faster at the top of the tower than at the bottom, and the difference was exactly what general relativity said it would be. This was, as Pound later described it, the experiment that ushered in the era of precision tests of general relativity. Before it, general relativity was a beautiful and theoretically compelling framework with some supporting astronomical evidence. After it, it was a tested, confirmed, experimentally established description of physical reality. The effect was not metaphorical. The effect was not approximate. The effect was exactly as large as Einstein's equations said it would be, measured in a building, with gamma rays and a loudspeaker, in 1960. Let that sink in for a moment. In a building on a university campus, using equipment that could fit in a small laboratory, two physicists confirmed one of the most exotic and counterintuitive predictions of 20th century physics. They proved that time runs faster at the top of a 22-meter tower than at the bottom. The difference they measured was less than 3 parts in 10 to the 15th, smaller than any ratio encountered in everyday experience. And they measured it. But a 20-meter tower in a Harvard building was only the beginning. To make the test definitive, and to connect it unambiguously to real-world applications, physicists needed to take their clocks beyond the building, beyond the city, and eventually, beyond the atmosphere. Part 5. The Airplane That Carried Time. In October of 1971, two scientists bought seats on commercial airline flights and brought luggage that no other passenger had ever carried. Joseph Hafele was a physicist at Washington University in St. Louis. Richard Keating was an astronomer at the United States Naval Observatory, the institution responsible for maintaining the standard of time for the entire country. Together, they carried 4 cesium-beam atomic clocks onto commercial airliners, flew twice around the world in opposite directions, and then compared their clocks to identical clocks that had stayed behind at the Naval Observatory in Washington. The entire experiment cost $8,000. $7,600 of that went to cover the cost of airline tickets for the physicists and, technically, for the atomic clocks, which occupied their own seats. It is one of the most inexpensive confirmations of a major physical theory ever carried out, and one of the most elegantly direct. The idea had come to Hafele while he was preparing lecture notes for a class on special relativity. He did a quick calculation on the back of an envelope. Cesium beam atomic clocks of the type available in 1971 were accurate to about 1 nanosecond per day, 1/1000th of a second. The combined effects of special relativistic time dilation from the airplane's velocity and gravitational time dilation from its altitude should produce a total time difference between a clock on the airplane and a clock on the ground of somewhere between tens and hundreds of nanoseconds over a round-the-world trip. That difference was within range of what the clocks could measure. He spent a year trying to get funding for the experiment, writing to funding agencies and getting politely turned down. Then he gave a talk on the subject and was approached afterward by Keating, who worked with atomic clocks professionally and who saw immediately that the experiment was feasible. The Office of Naval Research provided $8,000, and one of the strangest physics experiments in history was set in motion. The experiment was not simple even in principle. There were actually 2 separate relativistic effects operating simultaneously, pulling the flying clocks in opposite directions. The first effect was from velocity. Special relativity says that moving clocks run slow. The airplane was moving at several hundred kilometers per hour relative to the ground. At that speed, the special relativistic time dilation was small but measurable. A clock on the airplane ran slightly slower than a clock on the ground because the airplane was moving and the ground clock was not. But there was a subtlety. The Earth itself is rotating. A clock sitting on the ground in Washington is not actually stationary. It is being carried around the Earth's rotation axis at several hundred kilometers per hour. An eastbound airplane is moving in the same direction as Earth's rotation, so relative to a truly inertial reference frame centered on the Earth's center, the eastbound plane is moving faster than the ground clock. A westbound airplane is moving against the rotation, so relative to that inertial frame, it is moving slower. This means the time dilation from velocity is not the same for eastbound and westbound flights. The second effect was from altitude. The airplane flew at around 10,000 meters above sea level. At that altitude, Earth's gravitational field is slightly weaker than at the surface. In a weaker gravitational field, time runs faster, so the altitude effect runs in the opposite direction from the velocity effect for the airborne clocks. They both slow down due to their motion, but they speed up due to being higher in the gravitational field. The net result depends on the balance of these 2 competing effects. For an eastbound airplane, the velocity effect, slowing the clock, is larger than the gravitational effect, speeding it up, so the eastbound clock should lose time relative to the ground clock. For a westbound airplane, the velocity effect is smaller, because the plane is moving more slowly relative to the inertial center, so the gravitational effect dominates, and the westbound clock should gain time. The predictions from general relativity were specific. The eastbound clocks should lose approximately 40 nanoseconds. The westbound clocks should gain approximately 275 nanoseconds. These were not round numbers selected for convenience. They were derived from the actual flight profiles, speeds, altitudes, and durations of the specific commercial flights that Haffele and Keating booked. They included corrections for the fact that the flights were not at constant altitude or speed, and for the varying latitude of the flight path, which affects the Earth's rotation velocity. The eastbound trip began on October 4, 1971, and lasted about 65 hours, of which roughly 41 were spent in the air. The westbound trip began on October 13th and lasted about 80 hours, with roughly 49 hours of flight time. Haffele sat with his atomic clocks in coach class, monitoring them throughout both journeys, presumably fielding curious questions from fellow passengers about the large metal boxes occupying adjacent seats. When they came home and compared their 4 atomic clocks to the reference clocks at the Naval Observatory, the results were clear. The eastbound clocks had lost time, the westbound clocks had gained time. The differences were within the measurement uncertainties of the experiment of the relativistic predictions. The eastbound clocks showed an average loss of about 59 nanoseconds. The prediction had been 40 nanoseconds, with an uncertainty of plus or minus 23. The observed value was within error of the prediction. The westbound clocks showed an average gain of about 273 nanoseconds. The prediction had been 275 nanoseconds, with an uncertainty of plus or minus 21, nearly exact. This experiment was significant for several reasons. First, it confirmed both special relativistic and general relativistic time dilation simultaneously, using actual clocks that could be read directly. Second, it proved that the time dilation affected every kind of clock. Cesium beam atomic clocks operate on microwave transitions in cesium atoms, a completely different physical mechanism from the Mossbauer effect gamma rays of the Pound-Rebka experiment, but they showed the same effect. This was important because it ruled out the possibility that gravitational time dilation was somehow an artifact of specific measurement methods rather than a real property of time itself. Third, it set the stage for the most consequential practical application of gravitational time dilation in history. The GPS satellite system, developed through the 1970s and 1980s and made fully operational in 1995, could not function without the relativistic corrections that Haffele and Keating had helped confirm. The experiment with $8,000 and 4 atomic clocks on commercial airliners had, in some indirect but real sense, helped make possible the modern world's navigation infrastructure. Part 6. Your phone knows about curved time. There are currently more than 30 fully operational GPS satellites orbiting the Earth at an altitude of approximately 20,200 kilometers, completing 2 full orbits every sidereal day. Each one carries onboard atomic clocks accurate to about 20 nanoseconds. Each one continuously broadcasts its precise location and the time at which it transmitted its signal. Your phone, or your car's navigation system, receives signals from at least 4 of those satellites simultaneously, compares the slightly different arrival times of those signals to figure out how far it is from each satellite, and uses those distances to calculate its own position on the Earth's surface. The accuracy of the whole system depends entirely on timing. The speed of light is approximately 300,000 kilometers per second, or about 30 centimeters per nanosecond. If the timing is off by 1 nanosecond, the calculated position is off by 30 centimeters. For GPS to deliver the meter-level accuracy that your navigation app uses, the timing has to be accurate to within a few nanoseconds. Here is the problem that the engineers faced. The satellites are orbiting at 20,200 kilometers altitude. At that altitude, Earth's gravitational field is significantly weaker than at sea level. According to general relativity, clocks in a weaker gravitational field run faster than clocks in a stronger one. The satellite clocks should run faster than the ground clocks. How much faster? The calculation gives about 45 microseconds per day, 45 millionths of a second, every single day, gained by the satellite clocks relative to ground clocks just from the gravitational effect alone. But the satellites are also moving. They orbit at roughly 3,874 meters per second. According to special relativity, moving clocks run slower than stationary ones. At that orbital speed, the clocks would lose about 7 microseconds per day due to the velocity effect. The two effects partially cancel. The gravitational effect wins, and the net result is that the satellite clocks gain approximately 38 microseconds per day relative to clocks on the ground. 38 microseconds sounds trivial. It is 0.000038 seconds. Your reaction time when you hit the brakes is roughly 100,000 times longer. But in terms of GPS accuracy, 38 microseconds translates to about 11 kilometers of position error per day. Within a week, the position error would exceed 77 kilometers. The system would be completely useless. The design solution was elegant and permanent. Before the satellites were launched, the frequency of their atomic clocks was deliberately offset. The clocks were set to tick slightly slower than ground-based clocks by precisely the amount needed so that once they reached their operational orbit and began experiencing weaker gravity and moving at orbital speed, the combination of effects would bring them back into sync with the ground clocks. The offset frequency was approximately 10.229999543 MHz instead of the nominal 10.23 MHz. A difference of 4.57 parts in 10 to the 10th, smaller than the frequency difference between any two notes you could hear on a musical instrument, but sufficient, when maintained over the scale of an orbit, to keep the satellite clocks in sync with the clocks on the ground. It worked. GPS is accurate to within a few meters under normal conditions and to within centimeters with augmented differential techniques. The system is used by civilian navigators, military operations, surveyors, scientists studying tectonic plate motion, oceanographers tracking sea surface height, airlines automating approach and landing procedures, and power grid operators synchronizing the timing of electrical networks across continents. Every one of those applications depends on a correction derived from Einstein's general theory of relativity, not as a theoretical curiosity, not as an interesting background fact, but as an engineering specification built into the hardware of every satellite before it left the ground. The mathematics Einstein derived while working in a Swiss patent office in 1905 and 1915 is running inside the navigation satellite you just asked for directions. There is something almost philosophically striking about this. General relativity is often described as one of the most abstract and counterintuitive theories in the history of science, a mathematical description of space-time curvature accessible only to specialists with advanced training in differential geometry. But here it is, running invisibly in the background of everyone's daily life. The directions your phone gives you to the nearest coffee shop work, because space-time curves near massive objects, and because a young physicist had the audacity to work out exactly how it curves, and what effects that curvature has on the flow of time. When you check your location on a map, you are quietly confirming one of the deepest predictions of 20th century physics. You are, in a small and indirect way, running an experiment that Einstein would have recognized, and the answer you get, accurate to within meters, is the answer his equations give. The clocks are ticking at different rates all around you, right now. The clocks on the satellites overhead are running 38 microseconds per day faster than the clocks on the ground, corrected to sync with ground time by a preset frequency offset. The clock in your phone is running slightly faster than it would if it were a meter underground. The clocks at the core of the Earth are running slightly slower than the clocks at the surface. All of this, simultaneously, silently, as the ordinary background condition of existence on a planet embedded in spacetime. Part 7. The Earth's Hidden Secret. There is a fact about the Earth that Richard Feynman mentioned in passing during a lecture series he gave at Caltech in the 1960s. He described it almost as an aside, a curious implication of general relativity that most people had never thought about. He said that the Earth's core should be slightly younger than its surface. Younger not in the sense that the core formed later, because it did not. The whole planet formed at roughly the same time, 4.5 billion years ago, from the same collapsing cloud of gas and dust. Younger in the sense that time, over the billions of years since the Earth formed, has been running slightly more slowly in the deep interior than at the surface. And all that slower time, accumulated over 4.5 billion years, adds up. Feynman estimated the difference at a day or two. He was, as it turned out, quite wrong about the magnitude, though perfectly right about the direction. In 2016, a team of researchers, led by physicist Ulrik Ugerhøy at Aarhus University in Denmark, decided to actually calculate the number carefully, using modern computational tools and realistic models of the Earth's internal density structure. Their paper was published in the European Journal of Physics. The reasoning is exactly what you would expect from everything we have been discussing. The Earth's core sits at a depth of roughly 6,371 kilometers from the surface, the average radius of the Earth. The gravitational potential at the center of the Earth is considerably more negative, considerably deeper in the gravitational well, than the potential at the surface. The center of the Earth is surrounded by the entire mass of the planet, all of it contributing to the gravitational field at that point. A clock at the center of the Earth, sitting in that deeper gravitational potential, runs more slowly than an identical clock at the surface. The fractional difference in their tick rates is tiny, approximately 0.3 of a nanosecond per second, 0.3 of a billionth of a second every second, nearly undetectable in any brief measurement. But the Earth is 4.5 billion years old. That is roughly 140 quadrillion seconds. Multiply 0.3 of a nanosecond per second by 140 quadrillion seconds, and you get something around 1.5 years. For a simple uniform sphere model of the Earth. When the team used the preliminary reference Earth model, a more realistic description of the Earth's interior that accounts for the varying density of the mantle, outer core, and inner core, the number shifted to approximately 2.49 years. The Earth's core is, right now, today, approximately 2.5 years younger than the surface of the Earth. Every atom at the center of the planet has experienced slightly less elapsed time than every atom on the surface, not because something happened to them, not because they were somehow protected or delayed, but because the gravitational field they have been sitting in for 4.5 billion years is stronger, and in stronger gravitational fields, time runs more slowly. Feynman's estimate of a day or two was off by almost a factor of 1,000. The actual number is far more dramatic. 2.5 years of youth, accumulated in the dense iron core of a planet, over geological time, simply from the geometry of gravity and the structure of space-time. This fact has no practical consequences for geology or for the history of the Earth. The material at the core is the same age in the colloquial sense, formed at the same time, experienced the same temperatures and pressures and chemistry as the material at the surface. The 2.5-year difference is entirely a statement about elapsed proper time, about the number of seconds experienced at those two locations. Nothing in the Earth's core has been waiting, nothing has been paused. Time just ran slightly more slowly there, the way time always runs more slowly deeper in a gravitational field. And over 4.5 billion years, those slight differences added up to something you could, in principle, calculate and verify. This example is valuable not because of its practical importance, but because of what it demonstrates about the nature of gravitational time dilation. It is not a special case effect that only shows up in exotic environments, near black holes or neutron stars, or in space. It is happening right here, on the Earth we are standing on, inside the planet we have lived on our entire lives. The interior of your own world is younger than the exterior. The ground beneath your feet has been aging faster than the rock hundreds of kilometers below it. This is not a remote or theoretical truth. It is the condition of the place you call home, quietly in operation since the day the Earth formed. Part 8. Where time slows to a crawl. Neutron stars. When a star much more massive than the Sun reaches the end of its life, it does not go quietly. It collapses. The nuclear fuel that has sustained its core against the crushing weight of its own gravity for millions or billions of years runs out. The outward pressure of nuclear fusion disappears. Gravity wins, suddenly and catastrophically. The core implodes in less than a second, compressing from something the size of Earth to something the size of a city, accompanied by an explosive release of energy that briefly outshines every other star in the galaxy. The result is a neutron star, an object with roughly 1 to 2 times the mass of the Sun, compressed into a sphere approximately 20 kilometers across. The density inside a neutron star is so extreme that ordinary matter cannot survive. Protons and electrons are forced together under the pressure, combining into neutrons. The entire object becomes a sphere of neutron matter, a quantum fluid of densely packed neutrons, each touching the next, each pressing against the others with a quantum mechanical pressure, called neutron degeneracy pressure, that prevents the collapse from continuing. The density is comparable to the density of an atomic nucleus. A single teaspoon of neutron star material, scooped out and brought to Earth, would weigh roughly 4 billion metric tons. In terms of gravitational time dilation, a neutron star is a profoundly different environment from anything in our everyday experience. For a typical neutron star with a mass of about 1.5 times the Sun's mass and a radius of around 10 to 12 kilometers, the ratio of its Schwarzschild radius to its actual radius is something like 0.3 to 0.4. The star's surface sits reasonably close to where its event horizon would be if the mass were further compressed. This means the gravitational time dilation at the surface is significant, not a tiny correction but a real, measurable fraction. Clocks on the surface of a neutron star run roughly 1.2 to 1.4 times slower than clocks far away from it, depending on the specific mass and radius. That means that if you could somehow sit on the surface of a neutron star, which would be immediately fatal due to tidal forces, magnetic fields strong enough to break molecular bonds, and surface temperatures of around 1,000,000 degrees Kelvin, but, speaking hypothetically and ignoring those complications, every hour you experience there would correspond to roughly an hour and a half experienced by someone watching from far away. Your aging process, your heartbeat, every chemical reaction in your body, every process that constitutes the passage of time, would proceed at roughly 2/3 the rate as observed by a distant observer. Neutron stars are also where some of the most precise natural clocks in the universe are found. When a neutron star forms, the conservation of angular momentum causes it to spin rapidly, sometimes hundreds of times per second. During the collapse, the original stellar rotation is dramatically amplified, the same principle that makes a spinning figure skater rotate faster when pulling their arms inward, applied to a star collapsing from a sphere thousands of times larger to one with a radius of 10 kilometers. If the star's magnetic field is misaligned with its spin axis, the rotating magnetic field sweeps a beam of electromagnetic radiation, usually radio waves or X-rays, around the sky like a lighthouse beam. If the Earth happens to lie along the path of that sweep, we detect a pulse of radiation every time the beam passes over us. We call these objects pulsars. Their pulsation rates are extraordinarily stable, and the fastest spinning ones, called millisecond pulsars because they complete hundreds of rotations per second, rival the best atomic clocks on Earth in their precision over long timescales. Over periods of decades, some millisecond pulsars drift by only a few millionths of a second. Astronomers use arrays of them spread across the sky as a kind of galactic-scale timing network. For every pulsar in a binary system, the timing of its pulses encodes information about the conditions near it, including the effects of gravitational time dilation. When light from a pulsar travels toward us, it passes through regions of varying gravitational potential as the pulsar moves in its orbit around a companion. The changing potential shifts the arrival times of the pulses in ways that can be calculated from general relativity and compared to observations. These Shapiro delay measurements, named after Erwin Shapiro, who predicted this effect in 1964, provide some of the most stringent tests of general relativity ever performed. The observations match the predictions to fractions of a percent. The fastest known spinning neutron star, PSR J1748-2446 AD, rotates at approximately 716 revolutions per second. Its equatorial surface moves at roughly 24% of the speed of light. This adds a special relativistic time dilation component on top of the gravitational one. An observer on the equator of this object would be time dilated relative to a distant observer both by the gravitational potential of the star's mass and by the high orbital velocity of the surface itself. What the neutron star environment makes viscerally clear is that gravitational time dilation is not a subtle correction. Near the surface of one of these objects, it changes the flow of time by 30 to 40%. An observer on the surface and an observer in deep space are simply living at genuinely different rates, and neither of them is in an unusual situation from their own local perspective. The surface dweller's heartbeat feels normal to them. Their clocks run normally for them. It is only in comparison, when the two try to synchronize their watches, that the deep discrepancy becomes apparent. Part 9. The edge of time, black holes. There is a radius. For every mass, there is a specific, calculable radius, such that if you could compress that mass inside it, the escape velocity from the resulting object's surface would exceed the speed of light. Light itself could not escape. Nothing could escape. The object would become, in the most absolute sense, invisible and unreachable. This is the Schwarzschild radius, named for the German physicist Karl Schwarzschild, who derived the exact solution to Einstein's field equations, describing the space-time geometry around a spherical mass in 1916, just months after Einstein published the theory, and while Schwarzschild was serving at the Russian front in the First World War. He sent his solution to Einstein in a letter. Einstein was reportedly surprised that an exact solution had been found so quickly, and moved by the circumstances under which it was derived. Schwarzschild died months later from an illness contracted at the front. The Schwarzschild radius is given by a simple formula. It depends only on the mass of the object and a few universal constants. Twice the gravitational constant times the mass, divided by the square of the speed of light. For the mass of the Sun, roughly 2 times 10 to the 30th kilograms, the Schwarzschild radius works out to approximately 3 kilometers. The Sun is currently about 696,000 kilometers in radius, more than 200,000 times larger than its own Schwarzschild radius. It is in no danger of becoming a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. You would have to compress the entire mass of the Earth into a sphere smaller than a marble to form a black hole. When an object has a mass concentrated within its Schwarzschild radius, the result is a black hole. The surface defined by the Schwarzschild radius is called the event horizon. It is not a physical surface. There is nothing special about the material at that location. An observer falling through the event horizon would not feel a jolt, would not see a barrier, would experience nothing locally unusual at the moment of crossing, but they would have passed a point of no return. From that moment on, every possible path forward in space-time, every geodesic they could follow, leads toward the singularity at the center. They cannot turn back. They cannot send a signal outward. They are inside. For an observer watching from far away, the situation is different. And this is where gravitational time dilation becomes something more extreme than anything we have encountered so far. As an object falls toward a black hole and approaches the event horizon, the gravitational time dilation it experiences, as seen by a distant observer, becomes progressively more extreme. The closer the falling object gets to the event horizon, the more slowly time appears to pass for it from the distant observer's perspective. The object appears to slow down. Its emission of light becomes more and more redshifted as the photons it emits struggle to climb out of the increasingly deep gravitational well. At the event horizon itself, the time dilation factor becomes infinite. From the distant observer's perspective, the infalling object's clock has stopped. It takes an infinite amount of the distant observer's time for the infalling object to reach the event horizon. The object appears to freeze, becoming dimmer and redder as its emitted light is gravitationally redshifted, and the rate at which photons can escape to the distant observer drops towards zero. It does not cross the horizon as far as the distant observer can see. It asymptotically approaches it, fading into invisibility. From the perspective of the infalling object itself, nothing dramatic happens at the event horizon. its proper time continues to pass normally. It crosses the horizon in finite time, measured on its own clock. It proceeds toward the singularity. The infinite time dilation exists only from the external perspective. Locally, the infalling observer experiences time passing at its normal rate, unaware in any direct physical sense that they have crossed a boundary of no return. This is one of the deepest and most counterintuitive results in all of general relativity. The event horizon is not a place where time physically stops. It is a place where, from the external viewpoint, the flow of time has been dilated to infinity. An outside observer would have to wait forever to see an infalling object cross the horizon. In that observer's reference frame, the crossing never happens. In the infalling observer's frame, it happens in finite time. The practical consequence is that, as seen from outside, information from inside a black hole never reaches the exterior universe. Not because the black hole is opaque, but because the gravitational time dilation at the horizon means that signals from inside would take infinite time to reach an outside observer. The horizon is a causal boundary, a one-way membrane through which matter and information can pass inward, but from which nothing can pass outward. For the most massive black holes in the universe, supermassive black holes, with billions of times the mass of the Sun lurking at the centers of galaxies, the Schwarzschild radius extends to enormous scales. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of roughly 4.15 million solar masses and a Schwarzschild radius of about 12 million kilometers, roughly 17 solar radii. The one at the center of the galaxy M87, whose shadow was famously imaged by the Event Horizon Telescope collaboration in 2019, in one of the most dramatic experimental achievements in the history of astronomy, has a mass of about 6.5 billion solar masses and a Schwarzschild radius of approximately 19 billion kilometers, larger than the entire solar system. Near these objects, gravitational time dilation is not a small correction. It restructures the experience of time completely for anything that ventures close. In the immediate vicinity of the event horizon, the difference between the proper time of an infalling observer and the coordinate time of a distant observer diverges without limit. A civilization that somehow orbited close to the event horizon of a supermassive black hole for what felt to them like a single day could emerge to find that millions of years had passed in the distant universe. The galaxy they left could be unrecognizable. The stars they knew could have lived and died. This is not science fiction. It is what the equations of general relativity say would happen. It is what the same equations that were confirmed in a Harvard building with gamma rays, and in commercial airplanes with cesium clocks, and in orbit with the GPS constellation, say about the extreme limit of the effect. Part 10. The movie that got it right. In November 2014, a film was released that brought gravitational time dilation to the attention of a global audience in a way that no physics textbook ever had. Interstellar, directed by Christopher Nolan, was built around a science fiction premise, a wormhole near Saturn providing access to a distant galaxy. But within that framework, it depicted some of the most physically accurate portrayals of relativistic effects ever put on a cinema screen. The film was not merely inspired by real science. It was guided through the development process by one of the most distinguished theoretical physicists alive. The central emotional engine of the film was a scene involving a planet called Miller's Planet, orbiting dangerously close to a supermassive black hole named Gargantua. The crew lands on the planet and discovers it is covered by a shallow ocean producing enormous regular waves. They spend what feels to them like a few hours on the planet's surface. When they return to their ship and reunite with a colleague who waited in orbit, they discover that 23 years, 4 months, and 8 days have passed for him. Every hour they spent on the planet cost them more than 7 Earth years. The physics behind this sequence was overseen by Kip Thorne, a Nobel Prize-winning theoretical physicist from Caltech, who served as executive producer and scientific consultant on the film. Thorne did not simply endorse the film's science after the fact. He worked directly with Nolan during script development to ensure that the relativistic effects depicted were as physically accurate as the constraints of storytelling would allow. Their collaboration was so scientifically detailed that Thorne subsequently wrote a popular book called The Science of Interstellar, explaining in depth the physics behind each major element of the film, and his work with the visual effects team produced results significant enough for 2 published scientific papers. For the time dilation depicted, 1 hour on Miller's planet corresponding to 7 years elsewhere, the time dilation factor is approximately 61,320. That means time on the planet is running about 61,000 times more slowly than it does for a distant observer. Thorne worked backwards from that requirement to determine what the physical setup would need to be. To produce that level of time dilation, Gargantua had to be a near maximally spinning black hole. The spinning of a black hole, described by the Kerr solution to Einstein's field equations, creates additional gravitational effects that allow stable orbits to exist much closer to the event horizon than would be possible around a non-spinning hole. For a maximally spinning Kerr black hole, the innermost stable circular orbit can be extremely close to the event horizon, whereas for a non-rotating Schwarzschild black hole, the innermost stable circular orbit sits at 3 times the Schwarzschild radius, considerably farther from the horizon. By assuming Gargantua was spinning at very close to the maximum possible rate, Thorne could place Miller's planet in a stable orbit close enough to the event horizon to produce the enormous time dilation factor the film required. The planet would also be moving at a significant fraction of the speed of light in its tight orbit, adding additional velocity-based time dilation on top of the gravitational effect. Most physicists who have analyzed the scenario in detail consider the depicted dilation more extreme than what a stably orbiting planet could realistically experience, even around a maximally spinning black hole, and there are additional practical problems with the scenario, such as the intense radiation environment that's close to a black hole. But the qualitative premise, a world where time runs dramatically slower than in the wider universe because it sits deep in a black hole's gravitational well, is something Einstein's equations describe with complete mathematical rigor. The film also depicted, with remarkable visual accuracy, the appearance of Gargantua itself. The production team, working with Thorne's calculations, generated images of the black hole by numerically tracing light paths through the curved space-time geometry around a Kerr black hole. The resulting images, showing the accretion disk appearing both in front of and above and behind the black hole as light bent by the strong gravity looped around the hole, were so physically accurate that they prompted Thorne and his collaborators to publish 2 papers in scientific journals. One appeared in Classical and Quantum Gravity, describing the accurate visualization methods used and the physical phenomena they revealed, including some features of gravitational lensing near a Kerr black hole that had not been previously described in the literature. Interstellar made gravitational time dilation emotionally comprehensible to people who had never taken a physics class. The scene where the surviving crew member hands Cooper a stack of recorded video messages from his daughter, who has aged from a child to a middle-aged woman during the hours Cooper spent on a water planet, is not a trick of filmmaking. It is the correct emotional expression of what general relativity actually says would happen. The horror and grief of that scene come from physics, from the real structure of space-time, from the fact that in the universe we actually live in, gravity bends the flow of time. Part 11. The Twin Paradox and What It Really Means. There is a thought experiment in special relativity called the Twin Paradox, and it is famous partly because it sounds like a paradox, and partly because the resolution of that apparent paradox reveals something profound about the nature of time and motion. The setup is simple. You have 2 identical twins. One stays on Earth. The other boards a spacecraft capable of traveling at a significant fraction of the speed of light and departs on a long journey, eventually turning around and coming home. When the traveling twin returns, which one is older? The naive response is to say there is no answer. Relativity says all motion is relative. From the Earth twin's perspective, it is the traveling twin who has been moving. From the traveling twin's perspective, it is the Earth that moved away and came back. If everything is symmetric, neither should be older than the other. The apparent paradox is that each twin should see the other as running slow. But the situation is not symmetric. The Earth twin stayed in a single inertial reference frame throughout. The traveling twin had to accelerate. At the far point of the journey, they decelerated, turned around, and accelerated back toward Earth. That acceleration breaks the symmetry. The traveling twins' reference frame changed, while the Earth twins did not. There is a genuine, non-relative difference in their situations. The resolution is that the traveling twin returns younger, not slightly younger, potentially dramatically younger. If the spacecraft traveled at 99% of the speed of light for what the Earth twin measured as 10 years, the traveling twin would have aged less than 18 months. If the trip lasted 100 Earth years at 99% light speed, the traveling twin would have aged barely 15 years. This is not a paradox. It is a prediction. And that prediction has been experimentally confirmed, not with human twins, which would require spacecraft capabilities we do not currently have, but with subatomic particles. Muons are fundamental particles, similar to electrons, but about 200 times heavier. They are unstable and decay, with a half-life of about 2.2 microseconds when at rest in a laboratory. They are produced in the upper atmosphere by cosmic rays striking air molecules at altitudes of roughly 15 kilometers. At the speeds muons travel, close to the speed of light, classical physics predicts they should decay long before reaching sea level. The distance is simply too great for the short time their half-life allows. But enormous numbers of muons do reach sea level, far more than classical physics predicts. Because they are traveling close to the speed of light, their internal clocks are running slow from our perspective. Their 2.2 microsecond half-life corresponds to a much longer time in our reference frame. They live long enough to reach the ground, and when they arrive and we measure their remaining abundance, the numbers match special relativistic time dilation predictions precisely. From the muon's hypothetical perspective, the 15 kilometers of atmosphere is length contracted to a much shorter distance that the muon traverses in its normal proper time before decaying. The two perspectives, our time dilation and the muon's length contraction, give the same final answer, because they are different descriptions of the same spacetime geometry from different reference frames. This effect is not a curiosity. It is exploited in particle accelerators. Unstable particles that would decay in microseconds at rest are kept alive long enough to study by accelerating them to near-light speed, extending their lifetimes by factors of hundreds or thousands as measured in the laboratory frame. Without relativistic time dilation, modern particle physics experiments would be impossible. Now, gravitational time dilation from the curvature of space-time near a massive object is a distinct but related phenomenon. One way to understand the connection is through the equivalence principle, the bridge between the two. In general relativity, being at rest in a gravitational field is physically equivalent to accelerating in empty space. An object at rest in a gravitational field is, from the perspective of a freely falling observer near it, accelerating. That acceleration, by the equivalence principle, produces time dilation analogous to the velocity-based time dilation of special relativity. The deeper you are in a gravitational well, the greater the effective acceleration required to remain at rest there, and the more slowly time passes compared to a freely falling or distant observer. Both effects, the velocity-based time dilation of special relativity and the gravitational time dilation of general relativity, are aspects of a unified description of space-time. One arises from motion, the other from curvature, but they are both consequences of the same fundamental truth. Time is a dimension of space-time, and space-time can be stretched, curved, and distorted. The stay-at-home twin has taken the straightest possible path through space-time, a path with no acceleration, moving at constant velocity through one inertial frame. The traveling twin has taken a curved, kinked path through space-time, deviating from the straight line, curving away and coming back. In space-time geometry, the straight path between two events is always the longest one in terms of proper time, the elapsed time experienced on that path. By taking the curved, accelerated path, the traveling twin has traveled a shorter path through space-time. They have experienced less proper time. They return younger. This is the deep structural reason why gravitational time dilation occurs near massive bodies. Mass curves space-time. Objects moving through curved space-time follow geodesics, the straightest available paths in that curved geometry. But those paths, because space-time is curved, involve different amounts of proper time than the paths that would exist in flat, empty space-time. Objects deeper in a gravitational well, following their geodesics, trace paths through space-time that accumulate less proper time per coordinate time interval. They age more slowly. The physics is exactly consistent, and it is confirmed everywhere it has been tested. Part 12. The deepest question: what is time? We have traveled, in this video, from the GPS satellite correcting its clocks by 38 microseconds a day to the event horizon of a supermassive black hole where time dilation becomes infinite. We have seen the effect measured in a Harvard building with a 22-meter tower, confirmed by atomic clocks on commercial airplanes, embedded in the specifications of global navigation infrastructure, calculated to put the Earth's core 2.5 years behind its surface, depicted in a film by one of the most carefully scientific-minded directors working in Hollywood. The case is overwhelming. Gravity bends time. The bending is quantitatively precise. It is experimentally confirmed. It is practically consequential. But the deeper question, the one that gravitational time dilation keeps forcing to the surface, is one that physics has not fully answered. What actually is time? This is not a naive or childlike question. It is one of the most actively debated questions in the foundations of physics, and the existence of gravitational time dilation is part of what makes it so genuinely difficult. In Newton's picture, time was absolute and universal. It flowed at the same rate everywhere, providing a fixed backdrop against which all physical events occurred. This picture was intuitive, practically useful, and completely wrong. In Einstein's picture, time is one dimension of a four-dimensional space-time continuum. It is not a universal backdrop. It is a physical thing, something that interacts with matter and energy, something that curves, something that can run faster in some places and slower in others. Time has a geometry, the same way space has a geometry, and the presence of mass deforms that geometry. Time near a massive object is genuinely different from time far from one. Not just measured differently, genuinely different. But Einstein's general relativity describes time geometrically. It tells you how the geometry of space-time is shaped by the distribution of mass and energy. It tells you how clocks measure proper time along world lines in that curved geometry. It gives you the mathematical tools to calculate time dilation in any configuration of mass and space-time. What it does not do is explain, at a more fundamental level, what time is. Why does it flow forward and not backward? What makes the past fixed and the future open? Why do we experience time as something that passes rather than as a static geometric dimension like space? There is a deep puzzle in modern physics about the arrow of time, the fact that time appears to flow in only one direction. The past is fixed and the future is open. Memory points backward. Entropy increases forward. Causes precede effects. Every physical process we observe in daily life distinguishes the past from the future in a way that seems self-evident. But the fundamental equations of physics, including those of general relativity and quantum mechanics, are essentially time-symmetric. Run the equations of classical mechanics backward in time, and you get equally valid, equally permitted solutions. The laws do not intrinsically prefer forward time over backward time. The arrow of time appears to emerge from initial conditions in thermodynamics, from the fact that the universe started in a very low entropy state and has been evolving toward higher entropy ever since, rather than from any fundamental asymmetry in the laws themselves. Gravitational time dilation adds complexity to this picture. Near a black hole, the slowing of time near the event horizon means that different regions of space-time are genuinely running at different rates. There is no single, universal present tense that connects all of space at a given moment. What is simultaneous for a distant observer is not simultaneous for an observer near the horizon. The concept of a universal now, the idea that there is a single instant that is the present everywhere simultaneously, is not just approximately wrong, it is deeply, structurally wrong. This has profound philosophical implications. The block universe interpretation of relativity, favored by many physicists and philosophers of physics, suggests that past, present, and future all exist equally. The four-dimensional block of space-time exists as a complete geometric object. What we perceive as the flow of time is not an objective feature of the universe. It is a feature of our perspective, of our consciousness moving along a world line through that static block. In this picture, everything that ever happened and everything that ever will happen already exists. The Big Bang and the final state of the universe are equally real, equally present in the sense that different points on a landscape are all equally present to someone who has a map of the whole terrain. This interpretation is not universally accepted. Many physicists find it unsatisfying. It seems to drain the present moment of its reality, to turn the vivid, immediate experience of now into an illusion, a shadow cast by a particular location on a timeless geometric object. But it follows naturally from the geometric picture of spacetime that general relativity provides, and it receives support from the fact of gravitational time dilation. If different parts of the universe are running at genuinely different rates, if a clock on the surface of a neutron star accumulates less time per external second than a clock in deep space, then both clocks are real, both measurements are valid, and there is simply no single universal time that ties them together. Quantum mechanics adds additional complexity. The standard formulation of quantum mechanics treats time differently from space. Space appears as a full quantum variable. Time appears as a parameter, a background against which quantum processes evolve. This asymmetry is one of the deep tensions in foundational physics. Reconciling general relativity, which treats spacetime as a dynamical, curved geometry, with quantum mechanics, which treats time as a fixed background parameter, is the central unsolved problem of theoretical physics. It is what the search for a theory of quantum gravity is ultimately about. Various approaches attempt to resolve this tension. In loop quantum gravity, spacetime itself becomes quantized at the Planck scale, approximately 10 to the negative 35 meters, and the geometry of space and time emerges from a discrete underlying structure. Time, in this picture, may not be fundamental. It may be something that arises at large scales from a deeper, timeless description of reality. What we experience as the passage of time may be an emergent phenomenon, like temperature emerging from the statistical behavior of enormous numbers of particles, rather than a fundamental feature of the world at its most basic level. The physicist Carlo Rovelli, one of the founders of loop quantum gravity, has written extensively about the possibility that time, as we experience it, is not a feature of the fundamental laws, but an emergent effect, something that arises from the thermodynamic behavior of complex systems embedded in a universe with particular initial conditions. In this view, the flow of time is real as an experience, but not fundamental as a physical quantity. It is something that happens at a certain level of description, not something that exists at the most basic level. Whether any of these views is correct remains genuinely open. The physics of quantum gravity is not yet complete. The experiments that would discriminate between competing approaches are not yet possible with available technology. The Planck scale is 16 orders of magnitude smaller than anything a particle accelerator can currently probe. But the gravitational time dilation we have been exploring throughout this video points directly toward these deep questions. It tells us that time is not what we thought it was. It is not a universal river, the same everywhere, flowing at the same rate for all observers. It is a dimension of space-time, shaped by mass and energy, running faster in some places and slower in others, subject to the same kind of geometric distortion as space. And in that fact, in that single confirmed, tested, engineered into our infrastructure fact, lies a profound shift in what kind of thing time is. It is not a backdrop, it is a participant. It is shaped by matter, and it shapes the experience of everything that exists in matter's presence. You are, right now, aging at a rate that no one else in the universe is aging at. Your particular combination of position, velocity, and gravitational environment is unique. The proper time you are accumulating in this moment is something the universe has never produced before and will never produce again in exactly this way. The floor you stand on is aging slightly faster than the rock below it. The GPS satellite overhead is ticking slightly faster than the clock on your wrist. its speed and altitude balanced against each other to keep it synchronized with a world running at a different pace. The core of the Earth beneath you has been running just slightly slow for 4.5 billion years, patiently accumulating 2.5 years of youth it will never spend. Every second that passes for you now, here, in the gravitational field of this planet, at this velocity, at this moment in the universe's history, is yours alone. A unique quantity of elapsed proper time, different from the proper time accumulated by anyone anywhere who has been on a different path through the geometry of space-time. Not more or less real, not more or less valid, just different. The universe is full of clocks, none of them agree. And yet, somehow, everything holds together. The geometry of space-time, curved by mass and shaped by energy, orchestrates the whole thing, keeping the underlying laws the same for everyone, even as the rates at which those laws play out differ from place to place, and from observer to observer. Einstein gave us this. The Harvard Tower confirmed it. The airplanes with their cesium clocks demonstrated it in the most tangible possible way. The GPS satellites require it for their daily operation. The neutron stars display it at a scale of 30 to 40%. The black holes display it at infinite scale, at the event horizon, where from the outside perspective, time stops completely, and the infalling observer is frozen forever at the boundary between the universe we can reach and the one we cannot. Gravity bends time, and time, bent by gravity, reveals the universe to be something far stranger and far more personal than anyone before Einstein had any reason to suspect. If this video reached something in you, if it shifted even slightly how you think about the seconds ticking by as you watch, then this is the moment to click like and subscribe. There is so much more of this kind of deep, patient, immersive science storytelling coming, and I want you here for it. Leave a comment. Tell us where you are watching from, what time it is, what part of this landed hardest. Every single comment matters, and every one of them is a small proof that this kind of careful, unhurried science is worth making. Stay curious, stay comfortable, and we will see you in the next one. Quantum mechanics adds additional complexity to this picture. The standard formulation of quantum mechanics treats time differently from space. Space appears as a full quantum variable. Time appears as a parameter, a background against which quantum processes evolve. This asymmetry is one of the deep tensions in foundational physics. Reconciling general relativity, which treats space-time as a dynamical, curved geometry, with quantum mechanics, which treats time as a fixed background parameter, is the central unsolved problem of theoretical physics. It is what the search for a theory of quantum gravity is ultimately about. Various approaches attempt to resolve this tension. In loop quantum gravity, space-time itself becomes quantized at the Planck scale, approximately 10 to the negative 35 meters, and the geometry of space and time emerges from a discrete underlying structure. Time, in this picture, may not be fundamental. It may be something that arises at large scales from a deeper, timeless description of reality. What we experience as the passage of time may be an emergent phenomenon, like temperature emerging from the statistical behavior of enormous numbers of particles, rather than a fundamental feature of the world at its most basic level. The physicist Carlo Rovelli, one of the founders of loop quantum gravity, has written extensively about the possibility that time, as we experience it, is not a feature of the fundamental laws, but an emergent effect, something that arises from the thermodynamic behavior of complex systems, embedded in a universe with particular initial conditions. In this view, the flow of time is real as an experience, but not fundamental as a physical quantity. It is something that happens at a certain level of description, not something that exists at the most basic level. Whether any of these views is correct remains genuinely open. The physics of quantum gravity is not yet complete. The experiments that would discriminate between competing approaches are not yet possible with available technology. The Planck scale is 16 orders of magnitude smaller than anything a particle accelerator can currently probe. But the gravitational time dilation we have been exploring throughout this video points directly toward these deep questions. It tells us that time is not what we thought it was. It is not a universal river, the same everywhere, flowing at the same rate for all observers. It is a dimension of space-time, shaped by mass and energy, running faster in some places and slower in others, subject to the same kind of geometric distortion as space. Part 13. Clocks at the extremes, measuring the immeasurable. One of the most remarkable developments in experimental physics over the past 2 decades has been the extraordinary improvement in the precision of atomic clocks. A modern optical atomic clock, using transitions of strontium or ytterbium atoms interrogated by laser light, can achieve a fractional frequency uncertainty of around 1 part in 10 to the 18th. That is 1 part in a quintillion. To give you a sense of what that means in practice, such a clock would neither gain nor lose 1 second over a period longer than the current age of the universe. These instruments are not merely curiosities at the frontier of precision measurement. They are tools for probing the fabric of space-time in ways that were unimaginable even a generation ago, and they are allowing physicists to measure gravitational time dilation at scales that would have seemed impossible to the researchers who confirmed the Pound-Rebka result in 1960. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, achieved a measurement that demonstrated gravitational time dilation across a height difference of just 1 meter. Not 100 meters, not a Harvard building shaft, 1 meter. The height difference between a clock on a tabletop and one on the floor. At that scale, the fractional time dilation due to Earth's gravity is approximately 1 part in 10 to the 16th. A number so small that it requires optical atomic clocks of extraordinary precision to measure. They measured it. The result was consistent with general relativity. Time runs faster 1 meter higher in Earth's gravitational field by an amount consistent with Einstein's equations. In 2022, a research team published results from a new type of atomic clock that could measure gravitational time dilation across a vertical separation of only about 1 millimeter, using a cloud of strontium atoms held in optical traps at different heights. The ability to detect the space-time curvature of Earth across distances smaller than the thickness of your fingernail represents a remarkable compression of the distance scale at which relativistic effects are measurable. These ever-improving atomic clocks have opened up a new field of research, sometimes called relativistic geodesy. The idea is straightforward. Because gravitational time dilation depends on the gravitational potential at the clock's location, and because gravitational potential varies with both altitude and the distribution of dense material underground, an extremely precise clock can function as a probe of the local gravitational environment. 2 clocks at different elevations, or in regions with different subsurface densities, will tick at different rates. By measuring those rates precisely, you can infer information about the gravitational potential and therefore the density distribution of the Earth's interior, without digging. This is not merely a theoretical possibility. Several research groups around the world are working toward geodetic applications of optical atomic clocks. The vision is a network of ultra-precise clocks distributed across the surface of the Earth, each measuring the local gravitational potential with extraordinary precision, collectively providing a detailed map of the planet's gravitational field as it changes over time due to the movement of water, the deformation of tectonic plates, the melting of ice sheets, and other geological and hydrological processes. The clocks would not be measuring distance directly. They would be measuring time, and using the relationship between time and gravity to infer geometry. Einstein's abstract 1915 prediction about the relationship between gravity and time is becoming, in the 21st century, an instrument for monitoring the planet. The precision of these experiments also allows physicists to test whether general relativity is exactly correct, or whether it is an approximation to some deeper theory that agrees with it at tested scales but deviates at scales not yet accessible. Every precision test of gravitational time dilation that returns a result consistent with Einstein's equations extends the domain over which we know general relativity is at least an excellent approximation. Every such test narrows the space of possible deviations. If general relativity is wrong, the wrongness is subtle, below the sensitivity of the best experiments currently running. This matters because general relativity cannot be the final word. It breaks down at the singularity inside a black hole, where the curvature of space-time becomes infinite and the mathematics produces nonsense. It breaks down at the Planck scale, where quantum effects are expected to become important for the structure of space-time itself. There must be a deeper theory that reduces to general relativity in the appropriate limits, but adds new structure at extreme scales. What that deeper theory is, remains one of the great open questions of fundamental physics. Precision measurements of gravitational time dilation are part of how we will find the answer. If and when a deviation from general relativity is detected, it will show up first as a small anomaly in the most precise measurements of gravitational effects, including time dilation. The anomaly will need to be explained, and the explanation will require new physics. That new physics will, if we are fortunate, reveal something about the nature of space-time at a level deeper than Einstein reached. The Harvard Tower experiment that confirmed gravitational time dilation to 10% in 1960 was the beginning of a program of precision measurement that has no obvious end. We are measuring time dilation across 1 millimeter today. In 10 years, we may be measuring it across smaller scales still, or in configurations that probe aspects of curved spacetime that current experiments cannot reach. The more precisely we measure the relationship between gravity and time, the more clearly we will see the outline of whatever is waiting beyond general relativity. Part 14. The architecture of a curved universe. There is a way of thinking about all of this that pulls the various threads together into a single, coherent picture. It requires spending a moment with the geometry of spacetime itself, not with abstract mathematics, but with a physical intuition for what it means to live in a universe where space and time are unified in a four-dimensional structure that responds to the presence of matter. In flat, empty spacetime, the geometry is perfectly regular. Light travels in straight lines. Clocks run at the same rate regardless of position. Two people standing still relative to each other, separated by any distance, will accumulate identical amounts of proper time per unit of coordinate time. There are no preferred directions. There is no curvature. This is the flat spacetime of special relativity, the limiting case that applies in regions far from any source of mass or energy. Introduce a massive object and the geometry deforms. The massive object creates what physicists call a gravitational potential well, a distortion of spacetime in which the curvature increases as you approach the object. Clocks closer to the object run more slowly. Light passing near the object is deflected. Objects in motion near the object follow curved paths that correspond to the geodesics of the curved geometry. The surface of the Earth is not a flat part of spacetime. It is embedded in the curved spacetime produced by the Earth's mass. The curvature is gentle by cosmic standards, far more gentle than the curvature near a neutron star or a black hole. But it is real, and it is detectable. Atomic clocks at different altitudes tick at different rates. The difference is tiny, but it is there, exactly as Einstein's equations predict. Think of it this way. Imagine dropping a marble on a flat sheet of rubber. The marble rolls off to the side. Now place a bowling ball on the sheet. The rubber deforms, creating a depression around the bowling ball. Now drop the marble. It curves inward, following the deformed surface of the rubber sheet. This is the classic visual metaphor for how curved spacetime creates what we experience as gravity. The curvature of the rubber sheet is the curvature of spacetime. The marble's curved path is the geodesic that massive objects follow through curved spacetime. But this metaphor, as useful as it is, omits the time dimension. The rubber sheet model shows how spatial curvature can bend the paths of objects. What general relativity actually describes is the curvature of both space and time together, four-dimensional spacetime curvature. And it turns out that in most everyday situations, the curvature of time is a much larger effect than the curvature of space. For a weak gravitational field like Earth's, the dominant effect of spacetime curvature on the motion of slowly moving objects is the curvature of time, the time-time component of the spacetime metric. The spatial curvature is there, but it is suppressed by a factor of the velocity of the object divided by the speed of light, squared. For a falling rock or a planet, that factor is tiny. The trajectory is dominated by the curvature of time. What this means is that gravitational time dilation, the slowing of clocks deeper in a gravitational field, is not just a secondary consequence of general relativity. It is, in a very real sense, the primary gravitational effect for slowly moving matter. When you drop a ball and it falls to the floor, the reason it falls is that time runs slightly faster at higher altitudes. The ball, seeking to minimize the total space-time interval of its path, takes the path that goes toward where time runs slower. That path curves downward. The ball falls. Gravity, at its core, is the consequence of the fact that time runs at different rates in different places. Objects fall because they are moving through time, and time runs faster above them than below them, and their natural path through four-dimensional space-time curves downward as a result. The ball is not being pulled. The ball is following the curve of time. This is the picture Einstein arrived at in 1915, and it is the picture that the Pound-Rebka experiment, the Hafele-Keating experiment, the GPS satellites, the neutron star pulsar timing arrays, and the optical atomic clock measurements of the 21st century have all confirmed, at scales ranging from 1 millimeter to millions of light-years. Gravity is time, curved, or more precisely, the presence of mass-curved space-time. The time component of that curvature is what we experience as gravitational attraction. The spatial component produces subtler effects, including the deflection of light and the precession of planetary orbits, that require the full mathematical machinery of general relativity to calculate correctly. You live your entire life inside this curved architecture. Every step you take is a journey through slightly different rates of time. The floor of the room you are in is aging faster than a 0.1 kilometer underground. The top of a mountain ages faster than the valley below it. The atmosphere of the Earth is fractionally older than the ground it sits above. Every layer of the universe, at every scale, is a region of slightly different time rate, all of it determined by the local gravitational potential, all of it governed by equations that fit on a single line of mathematics. The universe is not a place where things move through time. It is a place where time is one of the things that moves, that curves, that bends, that slows and speeds depending on where you are. To live in it is to inhabit a four-dimensional geometry whose structure you have been completely unaware of for almost your entire life. And now, having followed the story from Newton's absolute time to Einstein's curved space-time, from a 22-meter tower at Harvard to the event horizon of a black hole at the center of a galaxy, from the principles of special relativity to the confirmed precision of modern optical atomic clocks, you know something about that geometry that most people walking the Earth today do not. You know that the clock you did not know you had, the one ticking in the room where you are sitting, is running at a rate determined by where you are in the universe's gravitational architecture. You know that there are other clocks, right now, ticking faster and slower than yours, all of them equally valid, all of them accumulating proper time at the rate that their position in space-time dictates. You know that gravity is not a force pulling things together, but a curvature of space-time that makes time run differently in different places, and that objects fall because they follow the natural paths through that curved geometry. You know that this is not speculation. It has been confirmed to parts per quintillion. It is running in the engineering specifications of the satellites overhead. It is written into the operational parameters of the GPS system that guides planes and ships and cars and hikers and search and rescue operations around the world. It is real in every way that physical reality can be real. And if you hold that knowledge quietly for a moment, not as an abstract fact, but as an experience, as something that is genuinely true of the room you are in right now, then you have done something that most human beings in the history of this planet never had the opportunity to do. You have understood, at least in outline, the architecture of the universe you live in. Part 15, The Long View, From Einstein to the Edge of Knowledge. The story of how gravity bends time is, at one level, the story of how a young physicist in a Swiss patent office overturned 2 centuries of assumptions about the nature of time with a thought experiment about riding alongside a beam of light. It is the story of experimental confirmation at a Harvard tower, on commercial airplanes, in orbit, and across the interior of the Earth itself. It is the story of how abstract theory became practical engineering and then became the daily operational reality of a civilization that navigates by satellite. But it is also, at a deeper level, the story of an ongoing investigation that is far from finished. We know with extraordinary precision how gravity bends time in the regime we can currently probe experimentally. We know that the relationship is described with great accuracy by Einstein's field equations, tested to many decimal places in contexts ranging from weak field solar system dynamics to the orbital decay of binary neutron stars radiating gravitational waves. We know that the practical consequences of gravitational time dilation are real and important enough to have been engineered into the global positioning system. What we do not know, and what remains one of the central unsolved problems of physics, is what happens to time at the most extreme scales. Near the singularity at the center of a black hole, where the curvature of space-time becomes formally infinite, general relativity breaks down. The equations produce divergences, quantities that become infinite in a way that signals the theory reaching the boundary of its applicability. Something new is needed, some deeper description of space-time that reduces to general relativity in ordinary conditions, but handles the extreme regime near singularities without producing nonsense. Candidates exist. String theory replaces point particles with extended objects and requires extra spatial dimensions, producing a framework that is mathematically rich and that may eventually provide a consistent quantum theory of gravity. Loop quantum gravity quantizes space-time itself, treating the geometry of space as something that comes in discrete units at the Planck scale, potentially eliminating singularities by preventing the volume from ever reaching exactly zero. Causal dynamical triangulations, asymptotic safety, twistor theory, and other approaches each offer partial glimpses of what a quantum gravity theory might look like. None has yet made confirmed experimental predictions that distinguish it from the others. What all of them share is the recognition that time, near the extremes of the universe's most massive objects, may not work the way general relativity describes. The infinite time dilation at the event horizon of a black hole, the formally stopped clock that a distant observer sees when watching an infalling object approach the horizon, may be modified in a quantum gravity framework. The singularity where time itself breaks down inside a black hole may be replaced, in the correct theory, by a more regular structure that general relativity cannot capture. Whether time is ultimately fundamental or emergent, whether it had a beginning or whether the Big Bang was preceded by something else, whether the laws of physics that govern the flow of time are the same throughout the universe or vary from region to region, these questions remain genuinely open. The fact that we can measure gravitational time dilation across 1 millimeter with modern atomic clocks, and the fact that we cannot yet probe the Planck scale where quantum gravity effects would become important, defines the gap between what we know and what we need to understand. That gap is the frontier, and the frontier is exactly where physics has always been most alive. The GPS satellite overhead is a monument to what Einstein got right. The unanswered questions about singularities and quantum gravity and the ultimate nature of time are a monument to what remains to be understood. Both facts are worth holding in mind, simultaneously, with equal appreciation. The universe has been generous in allowing us to probe its structure as far as we have, and it is patient, waiting for the next generation of instruments and the next generation of minds to push the boundary further. Every second that passes for you as you listen to these words is a second accumulated in your own particular gravitational well, at your particular velocity, on your own unique path through the curved geometry of space-time. Every second ticking in the atomic clocks on the GPS satellites overhead is slightly faster than yours, precisely corrected for. Every second on the surface of a neutron star somewhere in the galaxy is slightly slower than yours, ticking out the time of a dead star that went violent billions of years ago and has been keeping time since, as patient and as precise as any clock the universe has ever made. And somewhere, at the edge of what we can see and what we can calculate and what we can even ask coherent questions about, there are places where time itself does something we do not yet understand, where the rules we have confirmed with such precision stop applying, and where the next chapter of the story is waiting to be read. Gravity bends time, and the bending, followed to its logical extreme, leads to places where the story is still being written. If this video left you thinking about time differently, if it changed even slightly how you carry the seconds passing around you right now, then do one thing for this channel. Click subscribe and turn on notifications, so that when we go to these deep places again, you are with us from the start. Leave a comment below with where you are and what time it is, and if there is a topic you want us to explore next, something about the universe that has been living rent-free in your mind, tell us. The best ideas for future videos come from exactly the kind of person who watches something like this all the way to the end. Thank you for your time. In the most literal sense possible. Part 16. Living in Curved Time. A Final Reflection. There is a way this story could end that would feel incomplete, and I want to avoid it. I do not want to leave you with the impression that the bending of time by gravity is an exotic phenomenon relevant only in outer space, only in the realm of satellites and neutron stars and black holes. I want to make sure that as you close out this video, you carry with you something that is actually true about the specific moment and location you are in right now. You are aging at a specific rate that nobody else in the universe is aging at. Not approximately different, exactly different. Your path through space-time is unique to you. Every object in the universe with a different mass distribution around it, every object at a different altitude, every object moving at a different velocity, is accumulating proper time at a rate that differs from yours by some calculable amount. Most of those differences are infinitesimally small. Some of them, like the difference between you and a hypothetical observer orbiting a supermassive black hole, are enormous. But the point is not the size of the difference. The point is that the difference is real. The point is that time is personal in a way that Newton never imagined and Einstein proved. Every object in the universe has its own clock. Every clock is right in its own reference frame. And the universe never contradicts itself. When objects that have been on different paths through space-time come back together, they always find that their clocks agree on which one accumulated more time. The geometry is consistent, it always resolves. This is what I find most remarkable about gravitational time dilation, not the exotic applications near black holes, but the quiet fact that it is happening right here, right now. The ground beneath your feet is aging faster than the rock below it. The air above your head is aging faster than the air at your nose. The GPS satellite passing over the country is ticking faster than the clock on your phone. All of this, simultaneously, silently, as the ordinary background operation of space-time. You cannot feel it. You have no sensation of moving through curved time. Your nervous system did not evolve to detect the difference between a clock at sea level and a clock 2 kilometers up a mountain. The differences in everyday life are too small to matter to a biological organism, but they are real. And the instruments we have built over the past 60 years are sensitive enough to detect them, to measure them, to calculate them, and to engineer around them. The Pound-Rebka experiment measured a frequency shift of 2.5 quadrillionths across a 20-meter shaft in 1960. Today's optical atomic clocks can measure drifts 1,000,000 times smaller than that. The trajectory of precision measurement over the 6 decades since Pound and Rebka first proved Einstein right has been extraordinary, and it shows no sign of stopping. Future clocks will measure gravitational time dilation at still smaller scales, in still more demanding configurations, probing the relationship between gravity and time to depths that may eventually reveal the outlines of the physics that lies beyond general relativity. The universe is not finished showing us what it is. Einstein's theory is not the final word. It is a chapter in a story that is still being written, a chapter so precise and so confirmed that every sentence in it can be trusted, but a chapter nonetheless, followed by pages we have not yet learned to read. When you step outside tonight and look up at the sky and see the stars and possibly a satellite arc across the darkness, remember that everything you are looking at is doing something to time. The stars are surrounded by gravitational wells that slow the clocks at their surfaces. The satellite is ticking faster than the clock in your hand. The light reaching your eye from a distant galaxy left that galaxy after passing through regions where time was running at rates utterly different from the rate it runs at here. The universe is a place where time is constantly, everywhere, in motion relative to itself. And you are part of that. Your clock is one of the clocks. Your proper time is your own. Every second of your life that you have already lived was accumulated at a rate shaped by where you were and how you moved, by the gravitational field of the planet you have spent your life on, by the gravitational field of the star at the center of this solar system, by the gravitational field of the galaxy that contains that star. Einstein told us this. Pound and Rebka confirmed it. Haefele and Keating flew it around the world. The engineers who built GPS encoded it into hardware. The physicists who build atomic clocks that can detect it across a millimeter are extending its reach. And all of us, every day, live inside the consequence of it. Gravity bends time. You are living proof. So is every atom in your body, every photon from every star, every pulse from every pulsar, every tick of every clock in every satellite overhead. All of it, always, bent by gravity, into the particular time that each part of the universe experiences as its own. That is what time is. That is what gravity does to it. And that, after everything we have explored together in this video, is not abstract or distant or hard to hold. It is the most immediate and personal fact about the universe you could possibly encounter. It is happening to you, right now. If you made it here, thank you, genuinely. Subscribe if you have not. Leave a comment with where you are in the world and what time it is there right now. And we will see you next time, somewhere else in the universe. Part 17. The Numbers That Prove It All. Let us do something that science documentaries rarely take the time to do. Let us sit with the actual numbers that confirm gravitational time dilation. Because the numbers are where the physics becomes undeniable. Abstract arguments are compelling. Measured values are decisive. The Pound-Rebka experiment measured a fractional frequency shift of 2.57 times 10 to the negative 15 across a vertical distance of 22.6 meters. Einstein's prediction for this configuration was 2.46 times 10 to the negative 15. The agreement was within 10%. That does not sound impressive until you understand what those numbers mean. The gravitational acceleration at Earth's surface is 9.8 meters per second squared. The speed of light is approximately 3 times 10 to the 8th meters per second. Multiply the height by the gravitational acceleration and divide by the square of the speed of light and you get the fractional time dilation. For 22.6 meters, that works out to about 2.5 parts in 10 to the 15th, less than 3 parts per quadrillion. To measure that, you needed to resolve a frequency difference smaller than the frequency of light divided by 10 to the 15th. And they did it. The Haefele-Keating experiment. The eastbound clocks lost 59 plus or minus 10 nanoseconds relative to the ground clocks. The general relativistic prediction, combining the gravitational effect of altitude and the special relativistic effect of velocity, was 40 plus or minus 23 nanoseconds. The westbound clocks gained 273 plus or minus 7 nanoseconds. The prediction was 275 plus or minus 21 nanoseconds. Both results consistent with theory within measurement uncertainty. GPS satellites gain 45.9 microseconds per day from the gravitational effect of being farther from Earth's center, and lose 7.2 microseconds per day from their orbital velocity. Net gain, 38.7 microseconds per day. Without correction, position errors would accumulate at approximately 11.3 kilometers per day. With correction, meter-level accuracy. The correction has been built into every GPS satellite since the first operational constellation in the 1990s. The Earth's core, 249 years younger than the surface. Calculated using the preliminary reference Earth model for Earth's interior density structure, confirmed by the research of Ugerhøy, Mikkelsen, and Fay at Aarhus University in 2016. Gravitational time dilation on the surface of a solar mass neutron star with a radius of 10 kilometers, roughly 1.35 to 1.4 times slower than far from the star, depending on the exact equation of state. If you could spend a year on such a surface, Approximately 1.38 years would pass for a distant observer. Your aging would be 38% slower, as seen from far away. At the event horizon of a Schwarzschild black hole, time dilation is infinite. Zero time passes at the horizon, as measured by a distant observer, for any finite interval of the infalling observer's proper time. The infalling observer experiences their time normally. The external universe experiences the infalling observer as frozen forever at the horizon, asymptotically fading from view. These numbers span 25 orders of magnitude in the magnitude of the effect, from the subparts per quadrillion regime of the Pound-Rebka experiment to the infinite dilation at a black hole event horizon. And the same set of equations, Einstein's field equations of general relativity, describes all of them. Not a different theory for each scale. The same theory, applied consistently, giving the right answer every time it has been tested. There is no evidence of any deviation from general relativity's predictions in any experiment performed to date. That is a remarkable statement about both the accuracy of Einstein's theory and the ingenuity of the experimentalists who have tested it. The theory has been probed at scales from millimeters in laboratory atomic clock experiments to billions of light-years in the large-scale structure of the universe. At every scale, in every test, general relativity agrees with observation. That does not mean it is the final theory. It means it is correct at the scales we can currently probe. The deviations, if they exist, are hiding below the sensitivity of current instruments. Finding them, if they are there, will require the next generation of experiments and the next generation of theoretical ideas. But everything we have confirmed so far points to a single, consistent picture. Gravity curves space-time. The time component of that curvature slows clocks in deeper gravitational fields. The effect is real, measured, and consequential at every scale, from a laboratory on Earth to the most extreme gravitational environments the universe produces. Time is not what Newton thought it was. It is what Einstein said it would be. And it has been proven, over and over, with numbers precise enough to stake the navigation of the entire modern world upon. Part 18. A Letter to Time. There is a tradition in science writing, going back at least as far as Carl Sagan, of ending not with a summary of facts, but with something that tries to communicate why the facts matter. Not what we know, but what it means to know it. I want to try that here. We live in an era when the most abstract products of human thought, the equations written on a chalkboard by a physicist in 1915, turn out to describe the actual structure of the universe with more precision than any measurement we can make. This is a remarkable situation. There is no obvious reason why the universe should be comprehensible to creatures like us. There is no guarantee written into the nature of things that our mathematics should describe reality at all, let alone with this kind of precision. And yet it does. The equations that describe how gravity bends time were written before the instruments existed to test them. The prediction about the gravitational redshift of light was made decades before the Mossbauer effect was discovered, the discovery that made the measurement possible. The correction factor built into GPS satellites was calculated from theory alone, before a single satellite had been launched, and it turned out to be exactly right. Theory described reality before reality could be measured. This is what physicists mean when they say that mathematics is unreasonably effective in describing nature. The universe has a deep structure, and that structure is mathematical. Not in the sense that mathematics is a language we impose on the universe to organize our descriptions of it, but in the sense that the universe actually works according to precise mathematical relationships that we have been gradually uncovering for 400 years. Gravity bends time. The bending follows an equation. The equation is right. These three sentences together constitute one of the most significant things our species has ever learned about the place we inhabit. And the thing about learning how the universe works is that it changes you. Not in any dramatic way, not in a way you would necessarily notice from the outside, but quietly. You walk through the world differently when you know that the clock on your phone and the clock on the satellite overhead are ticking at different rates. You look at a mountain differently when you know that its peak is aging imperceptibly faster than its base. You think about a black hole differently when you know that, at its edge, the flow of time that carries you from moment to moment comes to a complete stop from the perspective of the outside universe. The universe is stranger and more detailed and more precise than ordinary intuition suggests. The strangeness is not threatening. It is, if you let it be, a source of genuine pleasure. The pleasure of understanding something true, of seeing a corner of reality that most people never look at, of knowing that the equations on a page and the satellite overhead and the atomic clocks in their laboratory cryostats are all describing the same thing, the same curvature of the same space-time, the same bending of the same time, in different contexts at different scales. Gravity bends time. You are inside that bending. You have been your entire life, and now you know it. That is enough. That is more than enough. That is, in a quiet and non-dramatic way, extraordinary.